For this video, I wanted to talk a little bit more about work and also then do an example where you're finding the work done by a couple different forces and then also thinking about how they might add up based on the conditions that were given. So first of all, I want to point out that work is our first physical example of how we could use the dot product or the scalar product to do a calculation. So we're told when we're introduced to work that it's the product of the magnitude of a force and a displacement, which we usually just call S, times the cosine of the angle between them. But when we look at that form, we might notice that that would be exactly the same thing that we would be doing if we found the dot product of the force dotted with the displacement. And that, in fact, is what we're doing here when we're calculating work. Keep in mind that the dot product or the scalar product gives us an answer that is a scalar. That means it doesn't have any direction. It just has a magnitude. It can be positive or negative, but that negative sign doesn't really mean anything because there's no direction attached to the work. And when I say it doesn't mean anything, I mean it doesn't mean anything about direction. So just looking at this picture, I want you to think about how this expression makes sense. So this is a pretty simple scenario where I'm moving a box along a flat surface from this location to this location. The way that I did it was by applying a force that's at an angle. So here you see all the different things that are used to calculate the work: the force, the displacement, and the angle. Now, what I want you to think about is if I sort of put these two terms together, the force times the cosine of theta, F cosine theta is really just the component of the force that is parallel to the displacement, which then makes sense because the other component of that force is exactly perpendicular to the displacement, which would be pointing up. And obviously, that component of the force is not going to do anything to get the block from here to there. It's not going to move it horizontally at all. In fact, the only component of the force that's going to help with this displacement is the one that's parallel to the displacement. And that's sort of a characteristic of the dot product, is when you take the dot product of two vectors, you're multiplying one vector, one magnitude of the vector, times the magnitude of the component of the second vector that's parallel to the first. Makes perfect sense that this is a good way for us to figure out the work done by a force. Now, let's turn our attention to a problem, and it's actually a problem from the back of your book. If you look at the last perusal assignment for Chapter 7, you can actually find this one. It's number 99. Now, we have an inclined plane here. I forgot to label the angle. The angle is 30 degrees. And there's this horizontal force that's being applied to the block that's going to help move it up the incline a distance of 8 meters. The block has a mass of 40 kilograms, and there is friction because we're given the coefficient of friction between the block and the inclined plane. It's 0.4. Now we're told that when this force is applied to the block and moves it up the inclined plane, it does so at a constant velocity. That's something that we want to keep in mind. With all that information in mind, we are asked to find the work done by the applied force, the work done by the frictional force, the work done by the gravitational force, and finally the work done by the net force. However, the first thing that we need to do is we need to figure out how big this force is because we're not told what it is. But one thing that we do know is that because this object moves at a constant velocity, it's in equilibrium. So not only are the sum of the forces in the y direction equal to 0, but they're also equal to 0 in the x direction. So let's take a look at some of these forces and remind ourselves that for an inclined plane, we orient the x and y axis so the x-axis is parallel to the incline and that the y-axis is perpendicular to it. Now I already have the force drawn. The other force that I have to think about is gravity, friction, and the normal force. So there's a lot going on there, so I apologize for that, but hopefully you are clear on what forces are that we're dealing with. So let's take a minute first and look at the forces in the y direction. In the y direction, we have the normal force, and we also have the y component of the weight. Oops, I did this when I did it on my own too. We have the y component of the weight, which is acting down. And remember that the angle between the weight vector and the negative y-axis is the same as the angle of the incline. So that angle there is going to be 30 degrees. And this is the thing that I forgot even the first time I went through this problem myself, was the applied force, because it's kind of a weird thing. We usually don't have a force like that, but in this problem we do, because it makes it a little harder. Now that force, when I think about relative to the x-axis, it's actually kind of pointing down. I should also realize that this angle is also the 30 degrees. So this is also going to be minus f sine of 30 degrees. And so here, my normal force is not just equal to the y component of the weight, but it's also adds to it is that a component of that applied force, which is f sine of 30, because at some level, that force is pushing the block into the inclined plane, increasing the normal force, which is in reaction to how hard that box pushes into the plane. That's the normal force is sort of reacting to that. So this I want to remember, because this normal force is used to calculate friction. Now, let's look at the forces in the x direction. I'm going to say up the incline is positive. So I have a component of that applied force, x up the incline. I have a component of the weight, which acts down the incline, and also the frictional force. So those are the three forces I have in the x direction. I can write the frictional force as mu times the normal force, and I already know what the normal force is. It's all that. It's kind of a pain. So let me step away so you can see it. Make sure you see it all. So all this right in here in the square bracket is just the normal force that I substituted in. Remember that my end goal is to actually figure out what the magnitude of this force is, because I can't find the first part of this problem, which is the work done by that force, until I know how big it is. What I want to do is I'm going to try to gather the terms that have the force in it and put those on one side, and everything else will go on to the other side. To get one of the terms for the force, I'm going to have to distribute this coefficient of friction times the second term, because that has the force in. So I'm going to just put these two expressions that have force in together. And I'm going to put the other two expressions on the other side. It's a lot. It's a lot of algebra, but it's not terribly difficult. I just want you to take a look at that. I've factored out the mg, trying to simplify things. But this is going to give me the magnitude of the force, which when I did that calculation, I found it was 498 newtons. And I'm going to write this up here, because as I continue with this problem, I need some room to work in. And so a lot of this stuff I'm going to want to erase. So I'm going to just keep up there where what I know was the force. And I'm going to try to get rid of everything else. I am going to keep the expression for the normal force, because I am going to be finding the work done by friction. And so I want to remember how I write that frictional force properly. So that is something that I might want to use later on. Everything else I can get rid of as I move on to really the meat of the problem. But notice I had to solve an equilibrium problem before I even started applying my knowledge of work to this problem. Okay, so I'm going to start looking at the values for the work done. So let's do, the first thing is the work done by the force. So I'm going to start off by just writing the general definition for work, where it's the force times the distance times the cosine of the angle between the force and the distance. Okay, so in this problem, I just found the force. It was 498 newtons. The distance is 8 meters. And now if I think about this drawing, the force actually is making a 30-degree angle with the horizontal. Well, doesn't look horizontal, but I guess what I should say is with the x-axis, and the displacement is along that x-axis. That's a long way of saying that the angle between the force and the displacement in this part of the problem is 30 degrees. And so when I work through all that, I get 3,450 joules. We learned that the unit of work are called joules. Now, for the second part, it's the work done by friction. Again, I'm just writing the general definition of work. And so I forgot to say this one is friction. So my work is the force of friction times the distance times the angle between them. Now the frictional force is mu times the normal force times the distance times the angle, cosine of the angle between them. And the coefficient, and then my normal force is right here. It was mg cosine of 30 plus f sine of 30. My distance is 8. Now this is a little bit tricky because the frictional force is down the incline and the displacement is up the incline. So the angle between the two is 180 degrees. When the cosine of 180 is just -1. So this answer is just minus mu times all that, which is the normal force, times 8 times a minus 1. Oh, sorry, I put the minus 1 out front, I forgot. The answer for that is that the work done is minus 1,883.5 joules. Now the reason that the work done by the the friction is negative is because the displacement is in the opposite direction from the force. So the force actually isn't really contributing to getting it up the incline, it's actually working against it. And that's why we have negative work. The third part is to find the work done by gravity, the gravitational force, which would be equal to, again, using Fs cosine of the angle. The force is mg, the distance is the 8, and now what's the angle between gravity and the displacement? Well, if we look at this picture here, the displacement is along the positive x-axis. And so to find the angle, we would measure all the way from that positive x-axis to where the force of gravity is, which is 30 degrees sort of offset from the negative y-axis. So I would actually use the angle that would be 90 degrees plus 30. So it's the cosine of 120. That is also going to give me a negative answer because the cosine of 120 is negative. And so when I put in the mass, which is 40 kilograms, the acceleration of gravity, I find the work done by gravity is minus 1,568 joules. Now I want to just show you another way to think about how I would find the work done by gravity, because it's kind of a neat way to think about it. So if I think of my box on the incline and it's moving 8 meters up the incline, and this is the force mg, I could actually think about how far did the block move in the direction of gravity, of that gravitational force, which actually would be this change in y. So this is a place where instead of thinking about the force that's parallel to the displacement, we've actually taken the displacement and paired it with the angle, and we're finding the component of the displacement which is parallel to the force. You can do that because all these terms are interchangeable, and you can sort of think of coupling any two of them together. So that change in y is going to be 8 times the sine of 30 degrees. But the delta y is positive and the gravity is negative, so the work is equal to minus mg delta y because of the fact that they're in opposite direction. But if you do that calculation, you're still going to find the same answer, which is minus 1,568 joules. So now, where am I going to stand? There's no room for me. Okay, I'm going to stand over here. Now the last thing that we want to ask is, what is the work done by the net force? You could do that two different ways. You could actually calculate the work done doing F times displacement times the cosine of the angle between them, and what you would put in for F would be the net force. But do you remember all that work I erased? The net force is 0 because this is a situation where we have equilibrium because of the fact that it was moving at a constant velocity. So the the work done by the net force is actually 0. We could also find that by adding all these, because these are all the forces that actually did work. And now if I add this work and this one together, I get 0. It's not exactly because of some rounding issues, but it's like the difference is either like 1 or less than 1, and so it's essentially 0. So you can see that I could find that answer to that last question 2 different ways. But in any case, I expect it to be 0, not only because the net force is 0, but if we start thinking ahead and remembering the new concept that we learned about the work kinetic energy theorem, because the kinetic energy isn't changing, the work is 0, because delta K, which is the change in kinetic energy, is 0, which is equal to the work, it's 0. All right, so I'm hoping that because we did a couple different types of forces and you saw different orientations, that this was helpful. And we'll see more of this stuff in class.